All right. We are back with vertical motion, 10th section in the notes. Um, we don't have too much more to go, but we are going to talk about vertical motion now. Okay, this has to do with like elevators and stuff, because elevators are kind of an interesting case in physics. Um, so let's talk about some vertical motion. So students stand on a scale in an elevator, and I need to point out something pretty important about scales. You may not know this, but did you know, fun fact, scale actually doesn't measure your weight? Okay, it doesn't actually measure your weight. It actually measures um, your normal force, or the normal force required to keep you on the scale, right? So when you step on the scale, right, the scale isn't actually measuring your weight directly. It's actually measuring the normal force that it has to exert on you to keep you on the scale. And so next time you go to the doctor's office and they say, "Hey, can you step on the scale to measure our weight?" You can go, "Actually, that gives you the normal force. You're not actually measuring my weight." And then they ask you not to come back, right? So the bottom line is that you have a student on a scale in an elevator. Elevator can accelerate upwards or downwards. The mass of the student is 50 kilograms, and then the combined mass of the whole system, student, elevator, and scale combined, is 500 kilograms. So big M. Okay. Elevator accelerates upwards at 2 meters per second. Okay. Draw a force diagram for the student in the elevator, and then determine the reading of the scale and the tension of the cord holding up the elevator. So the best way to do this, in my opinion, is I'm going to divide this into two problems. I'm going to do the scale, and then I'm going to do the elevator. Okay, so I'm going to start with the scale and I'm going to do the elevator. So the student, right, when the student is in the elevator, okay, he has two forces acting on him. He, of course, has mg going down, little mg, because he's just a student, but he also has normal force going up. Now, here's the thing that's important, okay? If the elevator is accelerating upwards at 2 meters per second, then the student should also be accelerating upwards at 2 meters per second, right? If he didn't accelerate upwards at the same rate, then either what would happen would be he gets crushed or he would start floating, okay? And he's not in creative mode, so that can't happen. So what's going to happen instead is he's going to have a larger force going up to give him that ability to accelerate upwards. So he has a net force going up, so he accelerates, okay? The elevator is also accelerating upwards, so that means that the tension force on it should be greater than the mg, right? Okay, so it's got tension force going up this way, okay? And then it's got mg going down, not as much. Capital Mg. Sorry, that should be capital Mg, okay? Okay, so for just the scale, right? For the scale, for the student standing on the scale, okay? We should see that there is a net force here, Fn minus mg, and we can set that equal to ma, right? Because net force is equal to ma. Okay? Well, now we have all the values. We just need to plug them all in. The mass of the student is 50. G is 10. Okay? Mass of the student is 50. And then acceleration is 2. So we just plug everything in. We've got F sub n minus, what is this, 500 equals 50 times 2, which is 100. Okay, well, what minus 500 gives me 100? Oh, 600. Okay, so the scale is going to this is the reading on the scale, right? Because I told you that the scale measures normal force. So the normal force on the student needs to be 600 newtons. That's what the scale is going to read. The elevator, you would do the same process, but this time instead of using Fn, you'd use Ft for tension. Okay, minus capital M G equals capital M A. Well, the whole system accelerates at the same rate, so all you would do is just do the same thing. Capital Mg, that's 5. That's 500 times 10 equals 500 times 2, and you should see that, okay, Ft minus 5,000 equals 1,000. Okay, well, that's pretty easy. It's just going to be 6,000. Okay, 6,000 newtons. Okay, beautiful. Okay, there's that. Okay, that's the elevator example. Okay, now this time, if we do the same way, but this time the elevator is accelerating downwards. Okay, so the next example says that the elevator accelerates downwards at 5 meters per second. This actually does change it up slightly. Okay, what you would notice is that now instead of normal force being the stronger force, it's going to be gravity. Okay, and then same for here. You're going to have some tension going up, but you're mostly going to have mg going down. Okay. Okay. And so the only thing that really prompts a change here, okay, the only thing that really changes here is the is that now what's going to happen, right, is your acceleration is directed down. It's just going to look slightly different. You would do mg minus the normal force equals ma. Okay. The only difference now is, of course, it's going to look a little bit different. So mg, right? So for the this is for the scale. Okay, and then elevator goes over here. Okay, so now I'm going to do mg. We already got mg for the student is 500. Okay, minus the normal force equals the m times a. So the mass of the student, which is 50, 50 times 5 is going to give us 250. Okay, and then you should be able to figure out from there that the normal force is equal to 250 newtons. Okay. And oh, why did I use negative a? That's just because you don't really. I mean, you don't. You could use it if you wanted to. That's fine. Um, that's that. If I guess we're considering the positive direction to be same with the acceleration. It's not a big deal. Okay, you would end up if you did it the other way. If you did Fn minus mg and you made the negative direction to be down, then and you did it the same way, you'd set it up Fn minus mg. You would use negative 250 and you would end up getting 250. Same thing for that. The signs would work out the same way too. For the elevator, you would do the same thing. So you'd have capital mg would be the first force that I would list here. And then you would subtract the tension force, and then you would set that equal to capital MA. And then what you would do is you would do this is 5,000, okay? 5,000 minus the force of tension, set that equal to the capital M, which is 500 times 5. That should be 25,000, or sorry, 2,500. And then you should see that tension force is simply going to be 2,500 as well. Okay, pretty easy. I mean, the numbers worked out really nicely, so it was just multiples of 10. Okay. Okay. Really quickly, this is so again, like I said, I added this part because of Alien Romulus, and going back to this idea that I haven't brought up since like the second lecture for here of the digital footprint, right? I saw the movie Alien Romulus, and there's a part in there in the movie that I was actually really impressed by, where they are they are in a spaceship. Okay, the crew is the main crew is in a spaceship. They're accelerating upwards, heading into space. And at one point, there's a character. Her name's Navarro. She says, here comes the crush, or brace for the crush, right? And as soon as that happens, as soon as like right after she says that, everyone feels this like big force. They kind of like jolt down. They feel this really big force pushing down on them. Okay, and so let me explain. And it says explain what Navarro means by that phrase and what happened. And I'll give you a hint. It's not because Kaylee Spaney appeared in that scene. She didn't, she did show up in the next scene, but when she said "Here comes the crush," she wasn't talking about Kaylee Spaney. Okay, she was talking about this phenomenon. Okay, well, the crew is accelerating upwards. So since the crew is accelerating upwards, okay, the normal force has to be greater than mg. Okay, so they feel this crush. They feel like crush, okay, because they feel heavier than normal. Now, this should make sense to you, at least conceptually, because the same thing occurs in elevators, okay? Same thing happens in elevators, okay? When you're in an elevator, you should notice that if you start on the ground floor and then the elevator moves up, you feel the jolt, right? You feel kind of like the jolt where you kind of feel that lurch, right? And then the opposite happens when you get towards the top. When the elevator is going up towards the top and it starts slowing down, you feel lighter than normal, right? That's the phenomenon of what we call apparent gravity. And you don't really need to know. I mean, you should know it, but it's not super, super important. Is this idea of apparent gravity? Okay, and apparent gravity is actually defined by a formula called GAPP, which is a gravity apparent is equal to G plus A if up is positive. Okay, so if you're accelerating upwards, then you feel heavier than normal. If you're accelerating downwards, you feel lighter than normal. Okay, and that's the phenomenon of apparent gravity. So if you're accelerating upwards, if acceleration is positive upwards, then then your apparent gravity is higher than normal, which makes you feel heavy, which makes you feel that crush. Okay. Okay. All right, Mr. Mitchell has a weight of 500 newtons, and it's actually kind of funny. Somebody pointed out to me that I made a typo, and I accidentally left this like you can see there's a little period right there, okay? And so it actually reads like Mr. Mitchell has a weight of 500 newtons. Also, somebody pointed out maybe it's like 0.500 newtons, so I'm just really light, which is absolutely not true. But I stand on a scale in the elevator, Stonebriar. It's a mall near where the school is. And I record the scale reading as a function of time because I'm a nerd like that. The data are shown in the graph above at time t equals 0. The elevator is at displacement x equals 0, velocity v equals 0. Assume that positive directions for displacement, velocity, and acceleration are upward. Okay, for the first part, draw and label all forces, not components, on Mr. Mitchell at t equals 8 seconds. Oh, okay, well, where is 8 seconds? Right about here. Okay. Okay, and did you notice? Oh, do you notice that the scale reading is higher than my actual weight? Okay. If my scale reading is higher than my actual weight, okay, that means that the normal force acting on me, that means that the normal force on me is acting greater, or sorry, is greater um, than that means that the normal force on me is greater than the mg. So here when I draw my forces, normal force is going to be really large up toward the top, mg not so much. Okay? So you would notice that, if I were to draw like the net forces, if I was to do like a Newton's second law equation here, I could do Fn minus mg equals ma. And if I calculate that out, you would actually see that my acceleration would be equal to Fn over m minus a. Or not a, sorry, g. Okay? Minus g. Okay? Which is kind of a fun thing for you to know. Okay? So notice that, okay? Okay. Sorry, I'm like collapsing my computer at the moment. Okay, what did I just do? Did I mess up my recording? Am I still recording? Am I still live? Okay. It's weird. I totally just opened the snipping tool on accident by hitting the print screen button on my computer. Okay, anyways, so there's that, okay? On the next page, it asks us to calculate the acceleration of the elevator for each 5-second interval. And the way that I would do that is using that equation that I just derived, okay? So for the first segment, right, it was, what was that equation I just derived? It was normal force over m minus g, okay? So what I'm going to do is for the first interval, okay, for a from 0 to 5, okay, then I'm going to do 500 over 50 minus 10, and you're going to notice that that's actually going to give you 0, so there's 0 acceleration in the first part, okay? What about in the second segment, from 5 to 10, okay, that gives us, what are we at? We're at, so sorry, the force reading on that one is 700, okay, over 50 minus 10, okay, and that should give me 4, okay? That would actually end up giving me 4 because 700 divided by 50 should be 14, minus 10 is 4. So it should be a positive 4 right there. Okay, and then what about for 10 to 15? Okay, for 10 to 15, it should actually still be 500 over 50 minus 10, which we saw earlier was 0. And then to get the final one, which is from 15 to 20, Okay, and by the way, I'm getting all these values from the graph. The graph tells me, the normal force I'm literally getting from the graph. 50 is the mass; it's constant, and then g is also constant. It's 10. Okay, for this last one, the should be 300 over 50 minus 10, and I actually get -4 from that one. So the acceleration is -4. So to plot the acceleration as a function of time, we have 0 acceleration for the first segment and 0 for this middle segment right here, but then it goes up to +4 right about here, okay? And then it goes down to -4 right about here, okay? So there you go. That's how you get that, okay? Okay, let's do the velocity. Okay, the velocity, the way I'm going to calculate the velocity is actually just using a kinematic equation. V equals AT plus V naught. Okay, that's how I'm going to do it. Well, if the elevator doesn't have any acceleration in the first part, then it shouldn't be going. So it starts at rest, right? And if it doesn't accelerate in the first 5 seconds, then it's not going to move at all. Okay. In the second set, so the second set, it has an acceleration of 4, +4, and it does this for 5 seconds. So its velocity at the end of that should be 20. Okay. Okay. Okay, what about for, sorry, that's at 10. What about the V at 15? Let's find out. Well, there's no acceleration, okay, from 10 to 15, so it actually shouldn't change its speed at all, okay? So it would just be 0 for acceleration times time, because there's no acceleration, plus the initial speed, or the speed that we started out in that segment with, which is 20, and so we should end up getting 20 again for that. Now for V20, for the velocity at time 20, okay, we would need to do the acceleration, which is -4 times 5, because it does it for 5 seconds, and then add to that the speed that we're already going, which is 20. Uh-oh, -4 times 5 is -20, so this should be 0, okay? When I plot this, we should notice, right, that it's 0 at the beginning, and then it increases up to 20 at 10. And it's linear, it's constant acceleration, so it should have the same slope the entire time. Then it doesn't change at all. It's flat there, and then decreases linearly down there. Okay? Okay, and to find the displacement, the last part asks for displacement. I think the easiest way to do the displacement here, honestly, is the easiest way, in my opinion, to do the displacement is literally to just take the area under the velocity graph, right? So right here, there's no area under the first one. So there's no displacement there, okay? Here we have a triangle. Our base is 5 and our height is 20. Okay, so 1/2 20 times 5. 20 times 5 is 100. Half of that is 50. So then the area here would be 50. Okay, so that means that from 5 to 10, we traverse 50 meters up. Okay, for this one right here, it's a rectangle. Base is 5. Height is 20. That's going to give us 100. Now, we're not going to put 100 under the 15. No. What we're going to do instead is we're going to put, we have to do, because we moved 50 in this part right here. Now we move another 100, so we actually are going 150. Okay, it's the total area, the total cumulative area. And then for the last part, it's another triangle, and it actually looks the exact same as the previous one. So it should be another 50, which is going to put us at 200. Okay, 200 meters. Okay, pretty straightforward. Oh, that's the first page of that. Okay, and then the graph is going to look kind of weird because it is going to have to, the concavity does actually matter for this one. Okay, for the first segment, right, we don't move at all. Okay, so I don't need to worry about that. We stay at 0. Okay. For this segment, we then have positive acceleration. So we end up getting to, where do we say, 50 at the end of this time period, and we have positive acceleration, so it should go concave up. Okay. Then when we go from 10 to 15, this is going to be a linear segment. Okay, because there's no acceleration, constant velocity. And then when we go from 15 to 20, we should end up at 200, and it should be concave down. And I'm terrible at drawing it, but hey, there it is. Okay. All right, that's vertical motion. Radical.